the concept or perhaps introduction to simple AC circuits. And I said this class here is the second part to that class, right? In today's class, we'll be looking at the idea of AC circuit, basically the components in full detail. Last class, I emphasized that when it comes to AC circuit components, there are three there. We have the resistor, we have the capacitor, we have the inductor. Alright, these are basically the components of an AC circuit we said in the last class. I'll drop the link to the last class in the description of this video. So check this video description, you see a link to the last class. So I believe you should know this. Now look up this. Look up. We said when it comes to AC circuit, there are three components: resistor, capacitor, and inductor. So this class here, we'll be looking at simple AC circuit containing only resistor. We'll be looking at simple AC circuit containing only capacitor. We'll be looking at simple AC circuit containing only inductor. I just picked them individually. Also, we're looking at AC circuit containing resistor and capacitor only. We'll be looking at simple AC circuit containing resistor and inductor only. Finally, we'll be looking at simple AC circuits containing resistor, capacitor, and inductor only. Let's start the first one. Let's start with AC circuits containing resistor only, please. Let's start with this. By the way, we define resistor as a device used for measuring the flow of current in a circuit, and we said the symbol for the representing resistor is either you use this concept, this one here, this is a symbol for resistor, or you use this one here. Sorry, use this one here. This one here is still a resistor. So either use this or this. It's still a symbol for a resistor. So aside this resistor here, there is one called rheostat. Rheostat. You have rheostat. So we have one called rheostat. It came from mind now. We have a resistor, right? There's one called rheostat. It looks like this. Look up. You see the same stuff there, but it has an arrow this way. This is a rheostat, or in this form too. This is still a rheostat, right? So there's one called a rheostat. So what's a rheostat? By the way, a rheostat is a value or change. So the value of a rheostat can be changed or alternated. That's simply a rheostat. So you see this, you shouldn't be afraid. This is a rheostat. This is what? A resistor. This is by the way. Now let's look at the main diagram of an AC circuit containing resistor only. So when an AC circuit contains resistor only, how does that look like? So look at this. This is diagram for an AC circuit containing resistor only. Resistor is this. So I can use any symbol. Let me just use this. Resistor is this. Alright, I have this. So I'll come here. This is VR. I have this one here. Alright. This is the diagram. F, V, F. Here's your resistor R. This part here is current R. So this is the diagram for AC circuit containing resistor only. This is diagram for an AC circuit containing resistor only. This VF, the VF there means voltage and its frequency, right? Voltage and its frequency, right? What's VR? Voltage across resistor. VR means voltage across resistor. What's I? I is current. We know that. What's R? The main resistor. The difference between R and VR. VR means voltage resistor, while R means resistor. So this is like the idea behind the diagram to a circuit containing resistor. The formula to note under the space. The formula to note under this here is that we know that from Ohm's law, we know that V equal to IR from Ohm's law. So express this man in terms of peak. This gives you V peak is equal to I peak in half. This is the formula you should note when it comes to AC circuit containing resistor only. For resistor only, what's like there? V equal to IR, please. IR, please. Your R is resistor here. So V equal to IR. So this is like the concept here. So this is for AC circuits containing resistor only. Let's look at AC circuits containing inductor only. Containing inductor only. Let's look at AC circuits containing inductor only. Inductor. Inductor only. Let's see. Let's look at a circuit containing inductor only. We said an inductor is simply a device used for storing electric energy, right? And we said the symbol for an inductor is just this one here, no big deal, right? And that's N. Right? No, resistor is R. Inductor is N, right? That's it for inductor L. This is an inductor. So let's draw a diagram. Let's draw AC circuits containing inductor only diagram. So it's similar to what I just drew earlier. I have this piece. Let me attach the resistor here. Then take it down. This part here gives you VL. The L here signifies inductor, please. I have this place. This is what? Voltage across inductor. Alright. So I have this place. Here is your VF as usual. Here is your current I as usual. Here is your L. Now here's the idea, please. Here's the idea. This is simply diagram to what's it called there? This is diagram for an AC circuit containing inductor only. I have a space. And this comes with no space, note space, note, no space. The opposition to the flow of current in inductor circuit, the opposition to the flow of current in an inductor circuit is called reactance. It's called reactance, right? And in bracket, that's what? XL. Is XL. Now listen. The opposition to the flow of current in an resistor circuit. The opposition to the flow of current in a resistor circuit is R. As I said, V equal to IR. But the flow, in this case, inductor, the opposition to the flow of current in an inductor is called what? The reactance. That's what? XL. The L is signifies inductor. That's XL. And mathematically, SL is given by 2 pi FL. So note that XL, which signifies the reactance. And what's the reactance? A reactance in this case is opposition to the flow of current in an inductor. And for inductor, XL is your 2 pi FL as the formula for XL here. In physics, there's what we call angular velocity, that's omega, but we know that omega is equal to 2 pi f. If you did wave, you can record this formula here, wave. This one is there in wave. So omega is 2 pi f. If omega is 2 pi f, I can express the reactance of an inductor, that is SL, as being equal to 2 pi f. This one here signifies omega, and I have L this way. It is still another expression for for the formula for an AC circuit containing inductor only. Now at this point, please also note the voltage across an inductor circuit, the voltage across an inductor circuit is known by the expression below. That's VL. Voltage in an inductor circuit is equal to what there? From Ohm's law, we said V is what? IR. Abi? In this case now, in terms of inductor, this becomes VL equal to current is still your current I. Then this resistor is no longer resistor because this is an inductor now. Right? So the resistor here, so this resistor is the opposition to the flow of current in a resistor circuit. Now, what is now the opposition of current in an resistor circuit? That's what? SL. So in this case, I'll not use what? SL here. So SL, so this is still an Ohm's law, but in terms of what? In inductor circuit. In terms of what? Resistor circuit is this. These are the concept behind AC circuit containing inductor only. Let's look at AC circuit containing capacitor only now. Let's look at AC circuit containing capacitor only. Let's look at AC circuit containing capacitor only, please. AC circuit containing capacitor only. AC circuit containing capacitor only. AC circuit containing capacitor only. If you like this video, please guys, do well to share it with your friends, like the video and leave a comment, and also join our channel membership to have access to exclusive videos of this nature. Alright, let's look at a circuit containing what there? Capacitor only. Capacitor only. Let's look at AC circuit containing capacitor only. So let's look at AC circuit containing capacitor only. What do we know? What do we know? So we know that for a capacitor, we have that the symbol. Okay, a capacitor is a device used for storing electrical currents in circuits, as we know. The The diagram for the capacitor is this. I submitted this before. Now, this is a capacitor diagram as I showed you on the board. So, so the symbol here is C. Inductor is L. Resistor is R. Capacitor is C. Please bear this man in mind. Alright. So I have this one here. So let's look at the diagram. How will the diagram of an AC circuit containing capacitor only look like? See the same concept. So I have this way. Capacitor here. This is C capacitor. Take this one down this way. I will have what there? VC. Voltage across capacitor. Alright. Move on down. I have this one here. I have this way. So this is your VF, and this is your current here. Current I. So this is your diagram for a resistor, please, for an AC circuit containing capacitor only. This is a diagram for an AC circuit containing capacitor only. And this one is note, please. Note, same concept. Note, please. Note. For the opposition, notice the opposition to the flow of current in a capacitor circuit. I said the opposition to the flow of current in a capacitor circuit the opposition to the flow of current in a capacitor circuit, the opposition of the flow of current in a capacitor circuit is known as the reactance. Right? And is simply, in this case, XC. For inductor, it was XL. For capacitor, because the capacitor is C, it becomes SC. Mathematically, here, what SC? Mathematically, SC is equal to the inverse of 2 pi FC. That's all. So for SL, it was directly 2 pi FA. In this case, it was the inverse 2 pi FC. What do we know? We know that omega is 2 pi F. This gives you that SC can be expressed as 1 over omega C. Alright, I have this one here. Also note please, the voltage flow through capacitor circuit, the voltage flow through a capacitor circuit is given by the equation below. Now we know that V is equal to what? IR. This formula is for any circuit containing resistor only. I have that VL equal to ISL. This one is Ohm's law in terms of resistor, in terms of any circuit containing inductor only. In this case, what there? VC equal to ISC. So it's more of like Ohm's law, but in different form. This Ohm's law originally in terms of resistor. This Ohm's law in terms of inductor. This Ohm's law in terms of capacitor. So the R here is resistor, the SL is CR, but the SL is called reactance. right? It's simply the opposition to the flow of current in an inductor. We have SL. The opposite flow of current is capacitor, is SL. The opposition to the flow of current in a capacitor is SL. So I is common, right? So the V, the VL, the VC is voltage in capacitor, VL voltage in inductor, and V is voltage in resistor circuit. Alright, this like we'll pick them in ones. Let's not pick them in twos. Let's look at AC circuit containing resistor and inductor only. It's not still one. Not still one. Alright. Let's proceed. So let's look at AC circuit containing resistor, and inductor only. So let me just save an space. So let's look at AC circuit containing resistor and inductor only. Alright. R is resistor, L is inductor. So let's look at this. The diagram for this concept here. So in this I have this resistor is this. I can use this for resistor. In this case, this is your resistor. Then inductor is this. That's L. I have this way. The diagram for AC circuit containing resistor only, resistor and inductor only is this way. Here gives you VR. Here gives you VL. It's inductor. So I have this one here. Call this one is it VF. So I have this. Alright, this is a diagram that shows the idea behind AC circuits containing resistor and inductor only. So I have this place. For AC circuits containing resistor and inductor only, please note, the opposition to the flow of current in an RL circuit, that is resistor and inductor circuit, is called the impedance. Is called impedance. In brackets, ZRL is called impedance. So the opposition to the flow of current in a resistor and inductor circuit is called impedance, and impedance is ZRL. So what's impedance? Mathematically, impedance that's ZRL is equal to the square root of R first. So R squared plus 1 there, L squared. This is formula for impedance, right? So in this case here, the resistor square plus the opposition for a resistor is R. The opposition for inductor is called the SL. So SL squared, right? So this is the formula for impedance when it comes to resistor and inductor only circuit. Also note in terms of voltage, in terms of voltage, That's V in brackets V. That's V what? RL. So VRL is equal to current I times what? Times what? The reactance, and that's what the ZRL. Alright, this is like what to note when it comes to a circuit containing resistor and inductor only circuits. Let's look at a circuit containing resistor and capacitor. Sorry, resistor and capacitor only circuits. Let's look at a circuit containing resistor and capacitor only circuits. Resistor and capacitor only circuits. So let's look at a circuit containing resistor and capacitor only circuits. Capacitor. So let's resistor and capacitor is this capacitor. I have this for capacitor. So here becomes VC is C. Alright, I have this with. Just change stuff. For you, you have to redraw it, right? Just change stuff here, save time. So any circuit containing resistor and capacitor only circuit is this diagram here. So note that, also note here, same thing. Note at this point is note the opposition to the flow of current in a resistor and capacitor circuit is called impedance. That's the impedance. Is it called impedance? And impedance is Z equal to R what? RC now. It's RC in this case. RC. Mathematically, impedance RC is equal to the square root of R squared plus what? Here because what the SC now. Because SC is the opposition to capacitor. R is opposed to what? To a resistor. So I have this formula here. So in terms of voltage, it's the same concept. VRC equal to what the I dot impedance R what the RC. This is the concept behind any circuit containing resistor, capacitor only. Finally, let's look at any circuit containing resistor, capacitor, and inductor only. Alright. Final part, let's look at any circuit containing resistor, capacitor, and inductor only. Let's look at any circuit containing resistor, capacitor, and inductor only. AC circuit containing resistor, capacitor, and inductor only. Let's work on this please. So the diagram obviously will be something of this nature. Diagram obviously will be this. Let's use for resistor, capacitor is this, and inductor is this. I have this please. Resistor, capacitor, inductor is this. Here gives you VR. Here gives you VC. Here gives you VL. Alright. Then I have my voltage frequency. That's V, F. Of course, current is always here. Current. I think the other diagram, I didn't put current. Attach current to the other diagram, please. The other diagram I drew, I didn't attach current there. Please put current. So I have this place. Now, at this junction, please note note please, under this please, note please. The opposition, the flow of current in an RLC circuit or RCL circuit in series RCL series circuit is called impedance. Is it called impedance? In bracket that becomes Z what? Z what? RCL. Mathematically, the impedance in this case now the impedance in this case, that's ZRCL, is equal to the square root of the reactant of each of them. That's R squared plus, in a bracket, SL minus SC. Alright, I have this please. This is the formula please. R squared plus SL minus SC. This is your formula for impedance when it comes to the reactant of resistor, capacitor, and inductor only circuit. Alright. Also note, in terms of voltage, in terms of voltage, that is V, I have that concept V equal to IR, Ohm's law. That becomes V, that's what V in what? RCL. Note what the I dot, the reactant here is impedance, and that's ZRCL. Alright, this is your voltage when it comes to a circuit containing resistor, capacitor, and inductor only circuit. Alright, let's look at two more concepts our copies. Let's look at two more concepts please. We'll come back. Let's look at these two last concepts and solve past question in the study of simple AC circuits. Let's look at the first part that says voltage multiplication. What's a voltage multiplication? This is also called Q factor. Please note that this man is also called Q factor. So note that voltage multiplication is also called Q factor. Definition: it is the ratio of VL to apply volt. What's VL? That's voltage across inductor, VL. So I said it's the ratio of VL applied VL to apply voltage. So I'm saying that Q factor, or voltage multiplier, is the ratio of what? VL, that's voltage across inductor, all over applied voltage, that's all over V itself. Right? So I want to proceed from here. What's VL? That's I, but we know that VL equal to I dot SL. Right? So put this man into this place. This is VL. What's VL? I dot SL. That gives you I dot XL all over. What's V? From Ohm's law, V to what? IR. So put IR there. This gives you IR. Alright, I have to think. From here, I will cancel I. I can express Q factor Q. Can also be expressed as Q as what? XL all over what there? R. That is, Q factor can also be expressed as, or can also be defined as, the reactant of an inductor circuit to each what? The reactant of a resistor circuit, as you can see. I have a space. And we know that XL, we know that XL is what? 2 by FL. So I can put this one here. Key factor can also be XL is 2 pi FL all over R. I have R here. This is still the same idea. This is the idea behind Q factor. Alright, this is the idea behind Q factor. This is the idea behind Q factor. Right? So let's look at, or you call it a voltage multiplier, or you call it a voltage multiplier. Let's look at resonance frequency. Let's look at resonance frequency definition. This is a frequency at which resonance occurs. The reactance in the inductor circuit is equal to reactance in the capacitor circuit. Now listen. When it comes to resonance frequency, the keyword or the idea there is that I'm equating the inductor reactance with the capacitor reactance. So for resonance to occur, there must be an equivalent, or there must be an equal inductor and capacitor. So I'm saying this. For resonance frequency, I have that SL equal to SC. You have this place. What do we know? We know that SL can be expressed as omega L, right? And SC can be expressed as 1 over omega C. I have this place. Let's start here. I can swap like this W, take W here, take L here. I'll have that omega dot omega equal to 1 over, this L comes in, LC. Omega times omega gives you omega squared equal to 1 over LC. Take the square here, become the square root. That gives you omega equal to the square root of 1 over LC. Apply such concept here. This can be expressed as omega equal to root 1 over root what there? LC. What root 1 is still 1. Root 1 is still 1. Right? Root 1 is still 1. From here now, what's omega? This gives you omega now is equal to root 1 gives you 1 all over root LC. By the way, I'm looking for the formula for resonance frequency. So, proceeding from there, alright, from there, we know that omega is what? 2 pi f. I mean, yeah, f. But in this case here, my f becomes fr. That's resonance frequency. You have to get resonance frequency here. This gives you so omega, that's 2 pi fr. 2 pi fr. Fr is resonance frequency. Is equal to 1 all over there, the square root of LC. At this point here, just bring these 2 pi down here. I'll have Fr, which is resonance frequency, is equal to 1 all over, bring these 2 pi down, it is 2 pi and then root LC. This is the formula for calculating resonance frequency. Alright, this is the idea behind resonance frequency. At this point, let's look at one last part called phase angle. Please know this one, it's very important. Know this phase angle. Phase angle number 1. Know the phase angle below. Number 1. For RL resistor inductor series circuit, the phase angle is given by on the board. Is given by on the board. Is given by theta is equal to tan inverse of xl over r. Number 2. Note number 2. For RC, resistor capacitor circuits, series circuit, the phase angle here, the phase angle is given by theta equal to tan inverse of xc over r. Finally, number 3. For RLC series circuit, that's resistor inductor capacitor series circuit, the phase angle in this case, is given by theta equal to tan inverse of xl minus xc all over r. So this is simply the phase angle you should note when it comes to simple AC circuits. With this stuff here, let's solve past question. So in our next class, we'll be looking at past question in the study of simple AC circuits.
I just launched a book called The Shortcut to Academic Success. In this book, I share a lot of experience on how I evaluated during my time in school. This method really helped me a lot. If you're interested in getting this book, simply chat me up through my WhatsApp number that is shown in the screen,